Good morning all and welcome to this seminar hosted by the Office of the Queensland Mine Rehabilitation Commissioner on erosion and landform evolution modelling. Before we get started, I would like to acknowledge the traditional owners on the land on which we're meeting today and pay my respect to the elders past and present. I'd also like to acknowledge that today is Remembrance Day, a day of national commemoration, and on this day at 11 a.m, Australians pause for a minute's silence to remember those, the bravery and sacrifice of all people who lost their lives while serving for Australia and its allies in wars and conflicts and peace operations. So along those lines, at 11 a.m, we will observe a minute's silence. A couple of housekeeping items. Today's session will be recorded. We also have the ability for you to lodge questions throughout the session. To do this, you can use the Q&A function in your top toolbar. All your questions will come to our team, and then we'll get to as many of them as we can throughout today's session. So with that all said, I'm now going to hand over to today's MC, our Principal Technical Advisor, Jason Dunlop. Over to you, Jason.
Thanks, Sam, and welcome everyone to this session on leading practice erosion modelling to design post-mining landforms. We know that this is one of the most challenging parts of mine rehabilitation. Building post-mining landforms is hard. Often we're dealing with materials that are dispersive and prone to high levels of erosion. We're seeing episodic rainfall events that can cause quite a lot of damage on these fragile systems. So the consequence of failure is high. And I think many of us have seen examples where a landform has been built and then over the years hasn't stood the test of time and has failed. When they fail, they can be quite expensive, having impacts on site and also off site to adjacent landholders. So it's something that we really need to be able to do the work up front and try and avoid down the track. So we know that the objective is to create stable landforms. So the three pillars of rehabilitation is to make land safe, stable, and non-polluting. So when we're talking about stability in this context, we're talking about a landform that doesn't have active eroding rills and gullies and doesn't have tunnel erosion as well. And we also want to make sure that any hostile materials are buried within the landform and not exposed into the long term so that they're covered and remain covered. So erosion modelling is critical to this process. The progressive rehabilitation and closure planning framework within Queensland now requires modelling to underpin the planning process, and there has been increasing use of modelling as a result. But it's a great tool. It provides a great way to test and compare different scenarios, and it helps you look at different options and refine your designs. It is complex though. It requires specialist skills and some careful consideration needs to go into it. So this workshop will talk through some of those issues that do need to be considered. We're going to look at the current approaches to erosion modelling and landform design. We'll talk through what is leading practice of erosion modelling, and then we'll talk through how to achieve leading practices in your own projects out there. So today's workshop will step through that guidance that has been published. We have a publication on the Queensland Mine Rehabilitation Commissioner's website that talks about this work, and I encourage you to have a look at that, download it, have a read if you can, and after the session. We will have a Q&A session at the end of each session, so we won't be waiting until just the end. We'll have a couple of stop points along the way, so please add any Q&A questions that you have into the Q&A function, and we'll bring those to the presenters along the way. And then we'll also have a Q&A right at the end to sum up. But before we jump into the session, I just wanted to give a little bit of background on our office. So many of you out there will be familiar with our office. We were established almost 5 years ago when there were amendments to the Environmental Protection Act in Queensland, and the establishment of a Mine Rehabilitation Commissioner came through in that process. So our vision is to lead Queensland to achieve best practice in mine land rehabilitation. And the Commissioner is an independent role. It's not regulatory. We're also not seen as the regulator of the regulator. We actually sit separate from the regulator. And our office has an advisory function. So key to that is bringing together stakeholders and connecting people to discuss mine rehabilitation issues. We also describe leading practice, which is the focus of today. And we also provide advice directly to the Minister for Environment, and we also report on rehabilitation trends and practices across the sector. We release an annual report on our website, and I'd encourage you to go and have a look at that. It talks about, the area of land disturbed versus rehabilitated land, and a whole range of interesting facts and figures in there. So I encourage you to check that out. So I wanted to introduce the speakers today that we have. We're really pleased for this project to have engaged Landlock to describe leading practices on erosion modelling and landform design. And the primary author is Dr. Rob Loch. And Rob is one of Australia's leading erosion research and management specialists. Rob has over 50 years of experience in research and management of soil erosion, soil conservation, and land rehabilitation. Rob's an emeritus consultant with Landlock and an adjunct professor with the Centre for Agricultural Engineering at the University of Southern Queensland. Rob's also a certified professional soil scientist and holds a registered soil professional accreditation in soil management and gully erosion. We also have Evan Howard with us today, and Evan's joining us from Western Australia. Evan is the Managing Director and Principal Consultant at Landlock. He has over 25 years of experience in the management of soils and mining wastes and soil erosion testing and modelling. Evan's also a certified professional soil scientist and has completed erosion assessments and modelling projects for mining clients across the world and across commodities, including coal, iron ore, gold and other metals, including bauxite and diamond and mineral sands. Evan has worked across Australia, the US and Africa, including temperate and tropical climates in Queensland. Evan manages the Landlock operations in Perth, and we thank him for his contribution. I also wanted to add a shout out and for the contribution that 3D Data Guidance made to this project, and in particular Lyndon McGrath from Landlock. It's also important to point out that the work that is prepared by experts to contribute to leading practice is externally reviewed by independent experts. And I wanted to thank Tim Nash and Evan Thomas in particular for reviewing this work and providing their feedback and input to it. So without further ado, I'll hand back over to Rob, and we can crack on with the presentation.
Thank you, Jason, and good morning, everyone. Now, today, our focus is on this recent publication. As Jason said, I hope everyone's downloaded it and had at least an initial look at the content. There's actually a lot of detail in that document, and we're not going to cover it all today, even though today we have got a hell of a lot of information to work through. Today, we'll focus on some quite key concepts that were identified and presented in that document, as well as going through aspects of how to assess and review landform design studies. The presentation will be in 3 sections. First, working through key concepts, and then applying the check sheet, which for how to review landform design studies, which is Appendix 4 in the report, and there should be time for a general discussion at the end. You'll notice the key concepts, which probably should have been obvious to us all, but some of them certainly reared their head or made themselves more obvious in the process of preparing this report. And the first being the importance of erosion model accuracy in mine site applications. I'll talk a little bit about models, the concept of ensuring that modelling is fit for purpose, introduce concepts of landform risk, and talk to target erosion rates for modelling. Now, erosion model accuracy Traditionally, when we've worked with erosion models, we've tended to immediately assume that a model prediction is accurate. So it's really important to understand that they're not necessarily all that accurate at all. But in the mining context in particular, accuracy matters a lot, which means that we require some rethinking of concerns with respect to accuracy. And in approaching modelling, we need to match particular model accuracy to site-specific requirements. And the reports that are produced need to actually talk to the issues of accuracy and how it's managed. So currently, erosion modelling for mine sites and for waste landform rehabilitation, the modelling is used to generate landform designs. Now, getting a mine design wrong can be very costly in terms of its impact on reshaping. Estimates from 3D data, for example, suggest that for a 200 hectare waste landform, if we decided our batter gradients were wrong by 2% and had to doze down from 17 to 15%, that'd cost nearly $800,000. And if in fact the difference was 4%, you're getting well over $1 million, 1.383 million. So the point here is that design and finalisation of a landform for rehabilitation does involve extensive and expensive placement and shaping of materials.
And I suppose at that point, I'd also add a couple of comments. In my experience in Western Australia, there's some examples where the cost of dozing down and reshaping are in the order of 80% of the total rehab cost for a site. And we've seen where the actual shape of the landform is designed, or at least built, so that it matches the final landform shape. That figure can be reduced to 30 or 40% of the cost. So the use of models is actually quite important and does have significant cost implications for mining operations.
There's also the point that mining is a fairly regulated environment, and for example, erosion simulations are now an essential component of progressive rehab and closure planning, PRCP developments, and the potential model erosion rates can affect project planning and approval. Delays to projects can be very, very costly. And so non-compliant erosion simulations as well, apart from the need to get them in the first place, but if they were found to be non-compliant, they also cost money and time. And I'd add that getting the design right is important, simply because generally repeating rehabilitation for a second time is often the most expensive rehabilitation that a site can do. So getting it right the first time is highly desirable. And overall, what we do need is we need there to be not just accuracy, but confidence in simulation accuracy when we work our way through these landform designs. When we look at the history of erosion modelling, we can see why essentially we haven't had that same pressure on accuracy of erosion modelling as we see when we look at mine sites. Initial erosion model development was strictly aimed at agriculture, extended to grazing and forestry, but typically erosion modelling was used to look at changing practices, occasionally maybe verifying that farmer Billy Bob Jones was likely to get some sort of a grant from the US government to make him more inclined to do the work. But we're talking an activity, agriculture, which relative to mining has a very low per hectare value, and the costs of the work are quite low in comparison. And so overall, the impacts of low model accuracy weren't of great concern. And there was, I might add, a perception that low accuracy was about all that was achievable, and that low accuracy was more than sufficient. So moving on and talking.
There was also an element, particularly in the agricultural setting, where there was the ability for ongoing management and maintenance of the land. And I think it's one of the key differences in the mining context, that there's often this perception or need for a set and forget approach, or you do rehab once and you don't have an opportunity really to go back and easily redo or rework or continually maintain land. And so the level of accuracy wasn't really needed because there was that ability to go and do fix-ups over time.
Yes, and that actually in the US, that explains why when they moved from maintaining cropping land to grazing land, their target or acceptable erosion rate was nearly reduced to a third to account for that lack of fix-up. Now, in terms of models, one of the concerns with models is that we want to see models used that are well validated, that we have some confidence in, and this means that they need to have been validated across a range of relevant materials, surface conditions, and mine sites. And I will talk some more about that further on in this presentation. The most commonly used ones are the revised USLE, which is a two-dimensional erosion model, empirical, statistical, and again, you'll get more on that. WEP, Water Erosion Prediction Program, which is process-based, two-dimensional, and then Siberia, which is process-based and statistical to a degree, but importantly, it's a three-dimensional landform evolution model. I might add that there will undoubtedly be more models thought about, trialled, and mentioned in the future, but for now, those three are the ones that are most dominantly used. Now, the revised USLE, which is the oldest, originally released as the Universal Soil Loss Equation, and they called it universal, they claim, the Americans, because when they put it together, they'd included finally all of the factors that affected erosion, and therefore it had a universal consideration of the eroding environment. So it was released, about the 1960s, late 50s, early 60s, and it was updated to the revised Universal Soil Loss Equation in 97. The model is statistical in that it was based upon a very large body of field plot data. As such, it generally fits the data, but for individual soils, its predictions can sometimes be quite poor. It does have limitations, including the very restricted range of soils that were actually tested. And we do find for soils with textures or properties outside that initial data set, studies have reported errors in estimates of soil erodibility by up to a factor of 3 or 4. Now, it does have quite simple parameters, and again, that really reduces its ability to cope with the enormous variety of soils and conditions. And it certainly has an issue with its consideration of slope length response, which doesn't necessarily pick up interactions between slope length and erosion process. Interestingly, the revised USLE originally was going to be released with 3 separate slope length response curves to try to address that smearing, shall we say, of a range of responses, but eventually, for simplicity, they just went with one. And the model structure does provide other limitations as well. Nonetheless, it's been the workhorse for many, many years, and it will continue to be used a lot. Now, the Water Erosion Prediction Program, it came out in the 1990s. There was a significant program of field parameter collection. There was essentially a circus of scientists and probably graduate students that went around the US carrying out experiments and gathering data and probably improving the turnover of the local bars somewhat. But it has got underneath it quite a significant body of field data. Now, it's a much more powerful and more detailed model. It's process-based. It's described as single event, but it actually runs on a daily time step because the Americans assume that you get one rainfall event a day, at least for modelling purposes. Now, the detailed erodibility parameters that are there are directly measurable, though, of course, given the data set that WEP's based on, it's got algorithms to predict the parameters as well. There was some dumbing down of WEP in terms of its input files, which was done to meet requirements way back in the 1990s. The model was expected to run for like 100 years of data on an XT computer for, I think it had to run in 90 seconds with the computer sitting on the farmer's kitchen table. So a lot of stuff was chopped out. Very few amongst you will remember an XT computer, but trust me, they were incredibly slow. So nowadays we'd wonder why all those functions were lost. But nonetheless, WEP gives very detailed output, and you can even get more accuracy and detail if you can get hold of the more detailed parameter files that were not originally released. They picked something very simple for use by their extension staff. Now, Siberia, and we're into a landform evolution model, and just for the record, Evan, a landform evolution model?
Yep. Well, it's a model that has an input elevation or DEM file, and the key difference, I suppose, between it and the other models is that that elevation is then changed through time. So what Siberia does is actually modify a surface through time in response to erosion. WEP or Russell just can assume the same slope each and every time.
Yes, and although there are versions of Russell and also of WEP that can be run on a three-dimensional basis, those versions have no ability to update a digital elevation model input. So this makes Siberia very valuable for looking at the impacts of flow concentration, gully development, depths of incision. It was released a few years earlier than WEP, but the interesting bit there's much interesting about Siberia. The maths under it can be quite complex, and Gary Wilgus, who produced it, actually won an Emil Truog Award for the best PhD in the US in the year that he presented his thesis and describing Siberia. Now, it's conceptually process-based, so there's a lot of data used and some fairly heavy stats to get parameters. If it is being fitted to field data, you do need to consider the length of record. A lot of studies have used input parameters taken from existing databases, which is great if you say it quickly, but there is and should be a concern whether those database parameters closely match the materials and the climate.
Yeah.
Now,
Siberia doesn't actually take in rainfall data. That's one of the things that we find is a misconception of the Siberia model. It's actually fitted to time series data of runoff and erosion, and doesn't actually have a rainfall file in it. So it makes it actually the parameters linked to both the material and the climate rather than just material-based parameters. So it's important that you definitely closely match the materials and the climate that's being considered.
And because there's so many different ways to parameterize Siberia in general, both in this presentation and the report, we've essentially viewed Siberia's accuracy as having a lot of potential variation, been a bit reluctant, shall we say, to categorise it. However, overall, if we look at model accuracy, and there's much detail in the report, especially for the revised USLE, and particularly for it, although we've suggested using plus or minus 50%, people do need to be aware that larger errors are possible. In this case, we've used that rating simply to flag that the accuracy is moderate at best, and then you do need to apply more stringent modelling targets. We see WEP with estimated parameters moderate, about plus minus 50%, and that was my view, and I was pleased to see Evan had a chatter with one of the WEP team, and that guy who'd done some extensive review of their parameter sets was again talking plus minus 50%. WEP with measured parameters we'd say has high accuracy, and we'll talk to that in a minute. And yes, Siberia we've got down as highly variable accuracy depending on its parameter source. So WEP with measured parameters. Now, I'll ask Evan to talk this because this is his data. Remind me, Evan, that very highest erosion point, that comes from a nickel mine I worked with?
Yeah, so it comes from a nickel mine, yeah. So
I'll come back to that one. It strangely enough, I get some pleasure out of it.
Yeah, I suppose we've just talked about there being algorithms within WEP that allow you to estimate parameters, and then the ability within WEP to actually put in measured parameters from lab or field studies. So this diagram or graph here shows times where we've measured annual erosion within the field, so using a range of techniques, and that might be erosion transects or measurements from LiDAR pickups, those sorts of things. And we've also got erosion predictions using WEP calculated for the same period. So the data set here is over 37 locations over a range of different climates. It includes arid zone and temperate, a range of different materials from quite sandy or loamy soils all the way through to quite rocky materials, and a range of slope shapes. So this data set includes uniform gradient slopes and also some concave profiles as well. So the lines there show the 95% confidence interval, and really it demonstrated for us that there is the ability through appropriate measurement to be able to accurately assess or accurately predict erosion using the WEP model. The next slide, Rob, if you could move on, is the same data, but instead of using the calibrated or the measured parameter set, we use the uncalibrated or the estimated parameter set. And I suppose the message or the lesson learned here is that the use of the internally derived parameters really provides a greater level of inaccuracy when looking at the predictions in the modelling. So that was certainly a lesson when we did this exercise to demonstrate how WEP and its accuracy can be impacted on the parameters that you feed into it.
Now, I occasionally used to scratch my head at why people were so intent on having predictive algorithms, but you've got the issue that particularly for erodibility, there's a view that measuring erodibility is too costly and slow. And because models are often used as extension tools, they might need to be able to walk onto a farmer's farm and virtually carry out a calculation on the spot. So algorithms, however, have not been a raging success. And that's essentially because whatever algorithm is fitted can't consider all of the soil factors that affect erodibility at a given site. You find with the USLE that they make an assumption that erodibility is driven by dispersed soil particle size. And strangely enough, when they tried applying the algorithms to aggregated soils, it all fell apart. So the problem you've got is that no algorithm is going to consider everything that matters, and so it can't work well. But that makes experimentation a much more attractive option, simply because you can go to the soil in question, apply rainfall and runoff, and find out exactly how it responds. There's also, for the USLE, a very restricted range of textures. In general, for erosion modelling and erosion model development, there's a real problem in terms of the shortage of baseline erosion, measured erosion numbers that you can compare against to prove whatever relationship or model you're trying to work on. And you've got to bear in mind that with particularly the USLE, but also with some of the others, the errors aren't just in terms of predicting erodibility, there can be other factors. And particularly for the models, the variations in erosion process and slope length responses associated with erosion process are sources of error. So I understand why people want to use algorithms and in some cases have to, but it really does guarantee that you won't be all that accurate. And now we're to the first point to pull up, and Jason.
Thanks, Rob. I think we've really covered a lot of ground there on the background of the models, the different models that are available and their utility, and then some of the levels of accuracy as well. So some really good content. We do have a question from Emma Ryan Reid, and thanks, Emma, for this question. It's a good one. How can Siberia address climate change projections if it doesn't have a climate input?
Yes.
You want me to take? I'll have a go first, Rob.
Okay, in that way, that Emma might get two slightly different points of view, and between the two, we might get a good answer.
Yeah. So I think there are ways for it to address climate change. The model requires the input or the use of a data set of runoff and erosion. Now that typically doesn't exist really anywhere, particularly if you've got a mined landform that doesn't yet exist. So one of the approaches that has been taken is to use other models such as WEP to generate that time series data of runoff and erosion, and by doing that, then fit the Siberia model to that. So to address climate change, it is possible to use other models such as WEP to do erosion predictions for a changing climate scenario, and then use the runoff and erosion outputs that it produces to create parameters that represent that changed climate. And in doing so, you're fitting that model to that changed climate scenario, and then being able to use that within Siberia to model evolution over time.
Evan, you stole my answer.
Oh, that's
great minds think alike, or fools never differ, they say.
Oh, we differ a lot, so we're safe.
Thank you. Another question we can jump into is how much modelling detail is enough, and when is it best to use a 2D model, and is it necessary to use a 3D landform evolution model all the time?
Okay. Typically, a 3D, well, often a 2D model is used as the initial working tool to look at slopes and to consider options. They're easier to parameterize, they're easier to run. Often as a final look at a landform, once you've got to the stage that you've got some sort of GIS person who's taken some vague statements about contours and gradients and put it into some great monster of a landform, that's the point at which you would run Siberia, in part to look at the issue of flow concentration, flow pathways, and this is where Siberia is used to make sure that those things don't happen. Equally, if you're really worried about incision of a cover layer exposing encapsulated materials, well, you would definitely run Siberia. If you had a relatively low risk landform, which might have been 10 or 15 or 20 metres high, made of something absolutely benign, growing in an environment where if you stood still for too long, you had grass growing on your boot, you probably wouldn't worry with running Siberia at all. So you would consider risk of the landform, and you'd consider what material, or where did I lose that? You would have to consider what sort of concerns you had, whether you were worried about incision or any flow concentration.
I think there's some slides coming up, Jason, that that will go through some of those things in a little bit more detail as well. Yeah.
All right. Excellent. We have one more from Melissa Salt, and the question is, do you consider an uncalibrated model is still acceptable to compare options in a relative manner? So i.e. Not accurate, but precise. Thanks, Melissa, for that question as well. Cheers.
Thanks, Mel, and good morning to you. The uncalibrated models have a role at different stages of project delivery, and they certainly can give options for comparing things, and in particular with, for example, the USLE, you may just pull out cover factors and use in comparing things. But there is a use and a place for uncalibrated models, very definitely.
Okay. Well, that's a good point to continue on. I think, Rob, we can keep moving through the slides.
Now, we come to the answer, start talking about the question. So basically, when you consider the stage a project is at, there can be situations, particularly early, where a model of low to moderate accuracy is quite appropriate. For example, in project planning, you may not have any capacity to go out in the site and dig up too much in the way of materials, or for that matter, any sort of samples. It might also be where the landforms are very low risk and possibly simple. So there are situations where you might be perfectly happy with a model of relatively low accuracy, such as an uncalibrated model. Now, if we take that a little bit further and put it into the context, we would think that for planning, the revised USLE, WEP, internally predicted parameters, and if you must, Siberia with database parameters would seem like an appropriate level of modelling to go into at that stage. Let's remember that if a project is still in the planning stage, it may not even happen. And so there is a practical length in terms of time, effort and cost that is worth expending at that stage. When you move to the point that a mine is actually seriously starting to move thousands or more of tons of cubic meters of material and starting to construct a landform, that's at the point where you would like to see greater accuracy because, for example, and Evan can talk to this one better than I can, it's a point at which if you know what the contours of your final landform are going to be, if you build to it, you can save an enormous amount of earthworks. Evan did touch on that earlier. And similarly, you might use Siberia with calibrated parameters, but in the first instance, you would certainly run WEP. And then
one exercise that we did a few years ago showing that that there was a six-fold difference in the actual cost of moving things around when you went from a poorly detailed designing to using the actual detailed shapes. So it can actually be quite a considerable amount of material and a cost that's involved in detailed construction. So that detailed design is also needed at that point.
Yeah, and then when finally we think about closure planning, there might be some review of WEP or Siberia modelling where you might look at parameter updates and maybe field validation of parameters if it's felt to be necessary. So the model that's appropriate obviously changes through the life of the project. And as just a comment, I asked about this one because my thought was, well, having talked about project stage for PRCPs and the like, what sort of project stages in Queensland mainly the subject of landform design using erosion modelling? And most of the landform design studies being submitted are associated with PRCPs, mostly from established sites, and would probably largely be classed as dealing with detailed design for construction. It might also, for example, be sites which are well established but might be thinking about starting a new pit or a new landform. That there's a significant number that talk to closure planning and some associated with new projects. The point of interest for me was that in general, the modelling and landform design work that's going on is dealing with sites that have been established long enough that they should have reasonably significant background information. So lack of information on the site, it should not generally be a major issue. And now we move to one of the interesting bits. We talk about assessment of risk. From the point of view of a modeller, risk is an important consideration. It affects what model the model is thought to be necessary because it talks to accuracy requirements and it does talk to target rates of erosion. So this is something that the modeller needs to know. And I'll talk through some of the target rates and you'll see more on that later, but assessment of landform risk, particularly as detailed in the recent document, has potential to be a major outcome and I think a major basis for communication about landforms between mine sites, consultants and regulators. Now, risk assessment's pretty clearly done on just about everything that moves and a fair bit that doesn't on mine sites. So having a comprehensive template for assessing landform risk isn't a great change or, shall we say, a totally novel idea. Now, the people will undoubtedly try to work out the lowest risk assessment that they can come up with, but I think the method here is reasonable and should give sensible ratings in when used appropriately. And I'd like to point out the little kicker in terms of target rates, that if you've got a high risk situation, then the target rates are reduced. And again, that shouldn't be too surprising. The simple analogy to that is the slow speed limit past a school. Just to give you an idea, this is covering off on what is in the report and talking about all of the issues to be considered. So it's a comprehensive list, and some of those factors are quantitative and will require some reasonable data if you're going to assess them properly. Others are more qualitative, so there could be some debate or disagreement on the levels, etc. there. But nonetheless, this list puts out a template, if you like, for sites to carry out a risk assessment and to collect sufficient and suitable data to address or to assess some of the issues that might be associated with their planned waste landform. So in terms of integrating the issues, you'd say 3 or more high ratings indicates a high-risk landform. But if you're 3 or more highest, we're all in medium, well, that's what you'd have. Now, a lot of emphasis on thorough assessment. And that is definitely going to be part of deciding whether or not the risk assessment is acceptable. But the other thing is that this risk assessment process should identify key issues of concern and should focus mine planners' minds on the management of those risks. And I'd even add that if having recognised the risks and discussing the consequences of them, which might be greater margins of safety in erosion targets or maybe a higher level of inputs required to manage risk, then the mine planner may well be encouraged to look for options that might be more cost effective and reduce the perceived level of risk. Now we come to the next checkpoint.
Thanks, Rob and Evan. That's great. We're covering off on, I guess, the need to consider the different level of modelling you might need at a different stage of mine life, how to consider the elements of risk, and you've stepped through the factors to consider there, and how to actually bring and describe how to bring those risk factors together and integrate them into an assessment. So I'd encourage you to publish your questions on the Q&A. We do have one here that says, how do we avoid confirmation bias, where the models are used to show that a design works rather than using models to tell us what the best possible landform design is? Probably a tricky one. More of a general.
It's a bit more general because I'm quite sure that there are many situations where a mine has a landform in mind and they'd like a modeller to prove that the landform they have in mind is going to work. If the modeller is worth their salt and the data are accurate, if the landform isn't going to work, well, the modelling should show it. Probably you will recall, folk, that I pointed out a high erosion point in the calibrated WEP output. That point related to a mine site where the rehabilitation manager had his preferred landform design, and it did not want to accept the landform design I suggested would be more stable. He went ahead and built his design, and it eroded actually at exactly the rate I predicted, which gave us a wonderful point to improve the regression on that particular graph. So I'm sort of a little concerned if a modeller simply sets out to fudge everything to prove that an inappropriate landform is more stable than it really is. That's the fault of the modeller, not the modelling.
I suppose it also comes back to the question around the parameters that you use, and we do later on in the presentation talk about confidence and when it gets to the review process, having sufficient information in the reports that we write that give the reader, which would mainly be the regulator, confidence that the modelling is worth its salt. So I think that through good reporting of what is actually being modelled, that confirmation bias could be highlighted and could then be questioned as part of that review process. And I think, yeah, well, as we touch on that, maybe that'll be a place where we can talk further about addressing things like confirmation bias.
Yeah, thanks. It was a really interesting point, and yeah, great comment. Thanks, Evan. We have another question, or perhaps a comment. So I'll just read through it, so bear with me while I run through it. But a mine site that is established will need to also consider the life of the asset and whether the design is at detailed stage or concept stage. For instance, a longer life of asset most likely would be at concept level design phase, whereas closure within a few years would require detailed designs.
Yeah, so I suppose the question there is how does that then impact the models that get used would be on my assumption.
Yeah.
Yeah. Yeah. I suppose the way that we're talking, it's you know, the difference between planning and construction really is that the period you have until you are actually developing those designs. I think if you have a longer mine life, then there would be some justification for using planning-based models in that longer time period where you're still really planning and looking at options for even feasibility studies, those sorts of things, using some less detailed models. But as the window closes, or I suppose the scope for adjusting things closes, then more detailed design may be required. I know there's some situations where I've seen rehabilitation might be a long way off, but it's or that it's got a long mine life, but because the way the mine is developing, getting access to that bit of land again is very unlikely. So now you're moving forward that period where you've got to actually have a detailed design. So I think that'd be just consideration of those sorts of things as well in terms of the model that you want to pick. In really, are you at that point where you really need to have some fairly high certainty in what you are going to implement?
Yeah. Yeah. Oh, that's a great point. And we have about 9 minutes till 11 when we'll pause. So we might crack on through the next section, Rob, and see if we can cover those.
That's my plan. So setting target rates for erosion modelling. Now, that seemed to generate a lot of discussion and concern in preparing the report, which puzzled me enormously because, as you see on this slide, target erosion rates, tolerable or acceptable soil losses, or T values even, was being talked about, and they were being used as far back for cropland modelling as 1947. Setting target rates has had a lot of discussion, and there's been all sorts of approaches that have been suggested, trialled, and with varying degrees of success. Now, early US focus was on maintaining cropland productivity. A rate of 12.6 tonnes per hectare, which conveniently is 5 tonnes per acre, was adopted for deep fertile soils. They were never going to be fertile forever at that rate, but they wouldn't hit the wall until long after everyone involved had shuffled off the mortal coil and was unlikely to be called to account for it. But that rate was reduced to about 4.5 tonnes per hectare for shallow rangeland soils because, again, of the inability to plough out rills, etc. Now, the problem or the challenge for what we were doing was to look at finding an approach that would, for the mine site situation, that could be applied fairly clearly and consistently across a wide range of mine sites, climates, and soils and whatever. So things like soil formation rate, no, too difficult and impossible to get a measure of something that's slow. And in some areas, the amount of deposition of dust was a complication. We really didn't think about natural soil erosion rates because they're highly variable, and they don't have a lot of relevance really to the modeller who's considering creating a stable landform out of a large mound of less than lovely unconsolidated fill, which even if it's eventually going to be stable, is never going to be a natural landform anyway. So we really had to look at what else we could find or what approach worked. So we specifically focused on preventing accelerated erosion due to development of rills and gullies. And that was selected specifically to contain on-site erosion to the relatively slow inter-rill process. We were very aware that if rills or gullies form, the change in erosion process gives you a quite dramatic increase in the rate of erosion. So that approach is quite consistent with other issues in the central Queensland area in particular, as for example, gully erosion has been clearly identified as a major source of elevated sediment concentrations and runoff from the Great Barrier Reef catchment. So equally for the mine sites, we were addressing the erosion process of greatest concern for that catchment. Now, interestingly, then also qualitatively basically exactly aligns with the current Queensland closure intent of no or limited rills or gullies. And in case you're pondering why we're so excited about rill and gully erosion, this slide shows old research of mine, published back in 1983, looking at erosion of black cracking clay under a very large rainfall simulator. And so we applied simulated rain to a range of plot lengths, and as plot length and discharge increased, at about 9 metre plot length, we saw the rills develop and sediment concentrations in runoff increased by about a factor of 3 or 4. And that sort of rate of increase or magnitude of increase in erosion with rill development has been reported quite widely. And certainly I measured it for quite a range of soils. So hence why we want to stay back at the nice low inter-rill level. Having thought through all that, and with the information that we had about the rates of erosion at which rilling and gullies developed, we've put together recommended target rates for modelling. And you'll see here, firstly, that there's provision for the targets to increase or decrease depending on the level of landform risk. So in other words, the target is a higher rate at a low risk, and it reduces to something quite low if the risk is high. The second point to be interested in is that we've put in not just a slope average erosion rate, but we've also included a maximum peak erosion rate at any point on a slope. And the reason for that is if we're concerned about initiation of rills and gullies, average erosion rates alone really don't tell a useful story. And the inclusion of peak rates at any point on a slope is really quite important. And note here also, come back. If using a model or parameters such that accuracy is low or moderate, then all of the above values should be halved. So we are taking into account both risk and model accuracy. Now back to the slide that you saw fleetingly. Gee, we're going to make it, Jason. So averages and peaks. Averages should be reported for distinct landform segments. They shouldn't be averaged across the landform segments that are distinctly different. And although the revised USLE only gives averages for a slope, I'll just flag that it is quite possible, if someone thinks hard, to take the USLE data and calculate peak erosion rates at slopes from the data that you obtain from the model. So the target rates help the modeler set a design. They're essential for modelling. A design developed to a specific maximum rate that is consistent with what's suggested has got a fairly good chance, but is not guaranteed to achieve what the regulator would like, because what's built is not going to be the same as what's modelled. And however, if the initial modelling uses a target erosion rate much higher or higher than what we'd consider stable, then the chances of the final landform being successful and free of rills and gullies is basically zero. And they won't achieve the regulatory requirement.
All right, great timing there, Rob. So as I mentioned at the start, the clock is just about to tick over to 11 a.m. So we will observe a minute's silence to reflect and to silently remember all of those who served and died in war. So I will just turn off all our cameras. We'll have that minute's silence, and then we'll continue with our presentation. Thanks everyone for that, for observing that moments of silence. I'll now hand back to Rob and Evan to continue with the presentation.
Okay, back we go. Now we come to the interesting bit.
Was there a pause for questions there, Jason? Did you want to pause?
Oh yes, actually, yes, please.
Yeah, sorry, if we can go back, that would be great. But just to reflect on the target rates and the use of the consideration of risk when identifying an appropriate target rate. I think that's a really good way to have a basis to compare between your modelling scenarios. It's not really intended to be a regulatory tool as such or a criteria. It's really about having something to be able to compare and contrast your model scenarios. I think that is a great addition, and it's something that we haven't seen before. So it's an excellent component of this leading practice. In terms of questions, we do have one that is a short one. Is there such a thing as a stable gully? It's a tricky question. Thanks for
that. Possibly. Back in the midst of time, certainly I put together a methodology for assessing gully activity and identifying whether the gullies were stable or not, and the degree, how active they were. But delving through the deep recesses of my memory, I seem to recall that some catchment studies found to their horror that gullies went through periods of nasty activity and then periods of quiescence. So quite often, if you've got a gully that is pretending to be stable, don't necessarily assume that it's going to stay that way. I think it was New South Wales Soil Conserve set up a catchment study, and their so-called stable catchment went feral on them about 1 year into the trial, with the gully just deciding to let rip. So under certain circumstances, maybe yes, but it would be relatively unusual.
I think maybe in the mining context, one possible situation might be as if the base of the gully starts incising into much less erodible materials. So if you've got like really blocky waste at the base, you might have a feature that forms rapidly, but then over time, because it's incising into less erodible material, the development of that gully is kind of ceased or stopped, and that's not really what you get in a natural environment. You often get like deep soils that cut through deep profiles of the same material. But that's probably the only place that I've seen gullies, like gullies rather than rills, stabilise. So
yeah, no, that's excellent. We have another one that is, shouldn't the target rates of erosion be also subject to local or undisturbed natural erosion loss rates in the region?
Hang on, sorry, could I have that one?
I'll just read it again.
Please?
Sure. Shouldn't the target rates of erosion be also subject to local or undisturbed natural erosion loss rates in the region? So I think it speaks to that, consideration of the natural erosion rates across the landscape.
You've got a whole host of problems, and we get a bit, people have been brainwashed a bit that if you say natural enough times, everyone starts to feel good. The natural rates of erosion occurring on a natural landscape, goodness, I swear I didn't touch that.
That's okay. You can leave it there, and we'll.
No. Now we're fine. I was just worried
that
I was freaked, Jason, because what was on my computer wasn't coming through in the screen. Just leave it. But the point here is that what we're building when we construct a landform on a mine site is not a natural landform. It's an unnatural landform with very, very different properties, and therefore It's not strictly or even closely comparable to what we see in a natural landscape. Typically, the gradients are different, the materials are different very often. The amount of, when you go down through the layers, what soil on a mine site landform can be awfully different to what's out there in a natural landscape. So, on what the finally, my system was freezing. We might have information on what is happening out on a natural landform, but we can't actually use that in designing what the what we're going to do with a waste landform.
Yeah, I think Rob, you might have some lag issues there with your
I do
computer.
have some terrible lag issues.
Yeah, but I think with natural erosion rates, I think Rob's right. Particularly in really flat, low gradient areas. I'm thinking like in coal mining, it's the natural erosion rates there are very, very low. And so you're having to then, if anything, if you're going to go that approach, then start to find generally steeper ground that might be like an analog. So then you're into different materials and the likes. So hence the approach taken was really to really keep it quite simple in that there's certain rates of erosion that are known to lead to rilling and gullying. And if we can model to that, then the design will have a tendency to then erode at rates that are not prone to rilling and gullying.
Yeah, absolutely. Okay, so we've covered a lot of ground in terms of the background and theory, and now we're going to jump into how to apply the check sheet and assess an erosion modelling report. So over to you, Rob.
Okay, so the review approach, and my approach to reviewing a lot of stuff comes from the time when I was getting an awful lot of journal papers, scientific journal papers to review for about 7 or 8 separate international journals. So it was a hell of an impost on my time, and the best outcome for me as a reviewer was to get something off my desk really, really quick. And the easiest way of that was to find what I would call a fatal flaw. A fatal flaw is something that was a failing in the work to the degree that no amount of editing or rewriting was going to solve the problem. Essentially, generally, it was a problem in the data. And so you had a fatal flaw which you could reject and say, nah, don't even edit this, just give up, go away and leave me in peace. So that is something that to be looked for with any report that comes in. Then there might be critical information gaps, and you can put in queries about that. And eventually, if you're working through that after various queries, and you might come to a response as a reviewer where it's a tick or a cross or a query. And sometimes what looks like a fatal flaw may be able to be addressed with a limited amount of work, but that wouldn't be certain. But the main thing here is that you're looking and you're thinking about what you're getting. Okay, so a broad strategy. The first thing is ask yourself, does this report address all the key issues? And this means go through, tick them off. Are they there? So the first question is, are they there? And then the second question is, are they really there? In other words, have the points been addressed adequately? And now this is where the review becomes a lot more challenging, but I'd suggest thinking of the analogy of looking at a tapestry and then looking for a loose thread to pull. There shouldn't be loose threads in a competent report. So you're saying, are the references relevant? Are the validations credible for models or whatever? Are Are all the decisions that were made justified by data? Is the decision process explained? Are parameters consistent with what was discussed in the document associated with this presentation? Is the modelling output credible? Now, we'll keep coming back to this point, that the report should present sufficient information in a form such that a reviewer can form a confident opinion that the report is credible. Now, it's not the reviewer's responsibility to get all that information. That's the responsibility of the person writing the report. So, modelling strategy. What should we see there in a report? We should see project stage identified, risks identified, and the level of risk identified together with the level of accuracy that's required. And that should be clearly stated. So the risk assessment should be thorough and cover all the listed issues. The models used should be stated together with the way in which they're applied, and is the model selection appropriate and credible? If, for example, somebody decides to use WEP as a landform evolution model, you're home and hosed and you've got a report off your desk straight away. But these are all questions that you need to ask and to see what has or has not been done. Next one, please, mate. So I'll give you some examples now. You might have a report that says we used a model, some strange model from somewhere, and it's been thoroughly validated, references. So the first point there is that if somebody wants to check the model, it's the author should supply the supporting references. It's not the job of the reviewer to thrash their way around the internet trying to get them, but the reviewer should then consider whether or not those particular references are credible. So you're talking about, are they independent? Have they been, is the work carried out for Australian conditions, mine sites? And does it cover a sufficient range of soils and conditions to be credible? A model applied and working really well for one soil in one condition is all very lovely, but it's giving you no confidence that it could be applied across a wider range of soils. And then again, there should be information on accuracy of the model. And if it's no information on accuracy, well, it's really not suitable for the mine site application that somebody wants to use it for. And if we move on to risks, the next question, are they identified? It can, a risk assessment may well become a somewhat complicated and less than a small task, but if it's done well, a risk assessment should cover the range of points. So have all the risks been identified, adequately investigated? Is there analytical data? And then does the design process really address the risks? Can or does the report verify and demonstrate that the modelling approach will address those risks? Now, I make the point here, I'll talk about the fact that a comprehensive landform design should consider quite a range of issues and risks. And the next slide is a little bit of an old favourite, and I apologise to those who've seen it too many times. But this was a trial where the opinion of an ecologist was that the rehab was a raging success because it was growing trees. Now, obviously, for those who wanted to see a stable long-term outcome, the amount of erosion and the lack of any other vegetation growing clearly was not consistent with a good outcome. So having a simplistic goal or adopting simplistic goals for landforms and landform designs actually adds to the risk. It doesn't address them. So next one, please, mate. There we go. Thanks, Sam.
That's great. We're a bit of a way into the checklist covering the fatal flaw approach and the focus on risks and discussion on model selection. I think it's really key that we have that description of the modelling strategy and the rationale and the logic that sits behind that described in the report, and we look for that. That's there. But I think at this point, Rob, we might just keep moving through the slide deck.
Yes, please.
Thanks.
Okay, model inputs. Now we come to the challenging bit. I keep saying that and it just gets harder. So this is where it's easy to be swamped by detail and to miss that your the reader is being blindsided. Now, this doesn't mean that somebody is deliberately set out to deceive at all. You might be effectively conned by the text, but to a degree, the person who wrote it probably was equally so. Often it's merely careless text and so on. So you really need to work methodically through the points and see if that in this slide, are they present? First question, are the relevant materials considered? You'd be amazed how often that's not right. Parameter sources, erodibility sources, time periods for erodibility parameters. If there was experimental erodibility measurements, how were they done? If it was database materials, were they demonstrated to be similar? And climate file records for the modelling. What climate file record was used, relevant to the site or not? So I'll give you some examples. Now, what we're going to try to do here is to demonstrate some of the things that people can look for. They may not be experienced at this, but try to illustrate the critical mindset that is applied. So first one, a couple of topsoil samples taken, and a bulk sample was collected for physical characterisation and erodibility measurement. The question there, how do you go with that? All sound fairly straightforward? Well, actually, personally, I would have given this a fatal fail. My first response was stockpiles. Which stockpiles? Are the particular stockpiles mentioned relevant? Were there more stockpiles that weren't mentioned? So you would want to have information provided on stockpile volumes to give you some idea of what's required to cover the landform. You would want to know their locations. You'd want to know sample locations. And you got the question, if you've got two stockpiles, but you only took a bulk sample from one, are you really sure that the two stockpiles were identical? And could you be sure? Say, for example, you had stockpiles that might have been 60 or 80,000 cubic metres. If we took one sample from each, would we be inclined to believe that sampling intensity was in any way meaningful or credible? Definitely not.
And so, even the sampling method is important. Was the sample taken just from the surface, like as a surface scraping from one spot, or was it taken through the profile of the stockpile at different depths? Those sorts of things would be useful information to know.
I can tell you that Landlock has received samples from a mine site where someone went out and sampled a whole heap of stockpiles, and despite instructions to the contrary, at about 10 to 20 centimetres depth, they took a sample from each stockpile, which was about 3 metres deep, in fact, and so the samples got to Landlock and were thrown in the bin, and we had somebody go back and sample properly. So first up, you really need to be sure that the sampling is adequate, and there has to be genuine proof that the materials considered are the materials that matter. So we go to the next one, please. And here we go again. This is different soil surface sampling, 4 locations across the site. So we're looking there. Soils broadly described as gravelly loams, gravel content 0 to 37%, and they ran the RUSLE nomograph. So we're then thinking about, are we okay with that? And the answer is no. Basically a fatal fail again. If we're considering a 1:25,000 survey intensity, which would be consistent with moderately intensive use of the soil at field level and detailed project planning, we would be looking at a sampling intensity there of somewhere between 5 and 25 hectares per sample. And if the material is variable, you'd be going closer to 5 than to 25. So we'd want to see a lot more samples. Equally, we really don't know what sort of sample they take. When they say surface soil, I can think of times we've received something was barely scraped off the surface, let alone dug in. And then we've got the other question. Is there any way that we can be sure that the surface soil samples had any relevance to what would be stripped for vegetation? So you would then actually, just for fun, ask them see if they had a nomograph for gravelly soils, because the rest of us don't. Okay, questions?
Okay, thanks for that. Do we have any questions from the audience there? If not, we probably can just keep going. It's some great content there. It's excellent to get this discussion on this. Hang on, we do have one there.
Oh.
From Thomas Baumgartel. Thanks, Thomas. Not every client for erosion assessment or reader of an erosion report is an expert. How can a certain level of quality be achieved in reports or erosion assessment work? So yeah, I guess thanks, Thomas. I think that really speaks to like the idea of, do you need to be an expert as a reviewer, or can you go and apply this checklist as best you can?
Well, the checklist gives you a starting point. The stuff we've talked about today gives you a starting point, and the text in the report does go through a whole heap of things that you could look for. Just based on what's in the document and what's covered today, I can certainly tell you that I could see a number of reports that I've seen would suddenly find themselves in the bin. But what we're working through, and I'm trying to give suggestions on how to think about stuff. We've totally agree that the issue of background knowledge is a problem for the reviewer, but short of providing advice and hoping that they take a lot out of today, given the detail we've provided, we have to hope that we've at least given them a hell of a leg up compared to where they were.
Yeah, it is a tricky part of the checklist, and I think it is a starting point. I think in that it steps out the questions that do need to be asked, and provides a basis for querying those as well.
I suppose it's also not something that's unique to erosion modelling. It's the same for any modelling, surface water modelling, groundwater modelling. The review process is needing at least a level of competence to pick the obvious errors to start with. I think one of the things that's been highlighted here by Rob is that some of the issues that are seen in the current erosion modelling is quite obvious, or fairly routine or obvious errors that can be picked by even the non-expert in the room as well. So.
Yeah, for sure. And I think if we do that, then we're lifting the standard dramatically. So that's a great thing. All right, we might move on, Rob.
Okay, Sam. Beauty. And then we get to the other one, the next bit. And again, I say things get more difficult again. But here are some clues. The strategy in this presentation is very much outlined in this, for providing help here is outlined in this slide. We accept the absence of hands-on experience, and there is the difficulty, which Thomas was quite aware of. So we're trying to identify key or essential components of experimentation. Try to at least identify the essential information that should be provided, and demonstrate some key issues, and even give a cheat sheet of some ballpark data that could be used as well. So for your next one. Sam, please. Oh yeah, sorry, you're ahead of me. With experimentally measured parameters. So clear statement of methods, photographs of test plots should be available if required. Experimental data should be shown. The one thing I would hate to see would be where somebody said, we done an experiment, this is the measurements we made, and here's the model output. And you think, oh, I think I didn't see something in there. So there should be experimental data shown, enough to verify the work. Calculations should be stated, parameter values reported, and all methods that have been outlined in the very first dot point should be consistent with good practice. And I know good practice is in the eye of the beholder, but nonetheless, it is important. Now, I'll give you an example here. An experiment to get wet parameters. So interval erosion measured on the erosion plot, set to a gradient, and rainfall applied for so long, timed runoff samples were collected, and the effective hydraulic conductivity of the soil is estimated to be 95 mils an hour. Next slide. I would normally have given a crowd a little bit of time to think about this, but let's move right on. So what are the things that jump out at me from that example? The first is the reference to the erosion plot. So there's a statement there that there was no replication. So that's not a good practice and not acceptable. So that's a fatal fail. Basing erosion model parameters and design of a waste landform on a single unreplicated plot is not good practice. Look at the rainfall rate of 95 mils an hour, which is not unusual, but we see that runoff happened because timed runoff samples were collected, which meant that the infiltration rate was less than the rainfall rate. Can we go back, please, mate? Thanks. Well done. Good. So we're in this situation that we've got infiltration of some sort and we've got runoff, and yet the hydraulic conductivity is 95 mils an hour, the same as the rainfall. Now, if you use the Philip infiltration equation, saturated hydraulic conductivity would be roughly the same as the long-term rate of infiltration. But if we know that our long-term rate of infiltration wasn't 95 mils an hour, well, then obviously that estimate of hydraulic conductivity is wrong, which is also a concern. And then if we think about it, we get another couple of concerns. First up, just back again, please. Thanks, Sam. First up, we're conscious that WEP doesn't use the Philip infiltration equation. The one that it does use, and I won't go through it, but will typically have an effective hydraulic conductivity somewhere between a third and a half of infiltration rate, depending on initial water content and possibly also particle size distribution. So when we see evidence that the person is trying to use an infiltration equation that isn't even the one that WEP works, we have to conclude that they haven't read the WEP manual, which is again of concern. And then we move to a final point, that the infiltration rate of apparently 95 mils an hour into a soil, and that is mentioned, it's a soil, is extremely unlikely, making the data even more improbable. And if infiltration rates appear unusual, certainly an experienced person would insist on seeing photographs of the plots under rain. Though, in this case, given the magnitude of other problems, pursuit of that information probably wouldn't be necessary. It's a matter of how many times or for how many reasons you really want for rejecting a report. Okay, next slide now, Sam. So now we look at one, and here we go, measuring rill erosion, assessed by applying varying flows to the overland flumes, which are set to a gradient, runoff samples. Calculated rill erosion rates were plotted against shear stress values. Yes, that's common. And the critical shear stress is 62 pascals, line fitted to 3 data points. So again, we ask, well, how do you feel about this one? And the first thing, again, we look at is to say, well, the highlighted words that jumped out at me, again, no replication. So not good practice, not acceptable, fatal fail. Typically for infiltrations and measurements and flumes, you would expect to see 3 replicate plots, not a single one. My second concern would be having an estimate of critical shear stress based on a fitted line that only went through 3 points. Really not acceptable again. So another strike. And then this one also has evidence that the modeller hasn't read the WEP manual, as the shear stress value is simply not realistic. And we can check that if we read the manual, which we'll show on the next slide, Sam. Yeah, here we have the cheat table. So this is in the user manual. Now, if we look across texture, soils, KI, KR, and then tau C. Tau C is short for critical flow shear stress for the initiation of rilling. And the values in pascals there actually go from about 2.1 to 5 pascals, which is a long way short of 62. You will get higher values if soils are consolidated by wetting and drying cycles, but the value quoted in the previous slide is basically way off the scale. And this table does allow you to look at the values, because there is KI is inter-rill erodibility, KR is rill erodibility. So this is an opportunity for anyone to check whether the parameter values that have been derived are at least within the ballpark. Remember, these are values that you get out of the WEP internal algorithm, so you might view them as plus minus 50%. The next slide, please, mate. Right. And again, checking adequacy. And so we don't just pick on people using WEP, Siberia parameters. And parameters developed previously for a similar material were adopted for this site. Sounds fantastic if you read it quickly. But if a practice nitpicker gets hold of it, your first question is, well, parameters. What parameters? How'd you get them? You would then say, and if you got them from field data, tell us about the duration of measurement, rainfall during that period. Was it consistent with the long-term average? How did you determine similarity? What properties of the material were considered? You're then talking about if there was a difference in annual rain amount between the 2 sites, how was that accounted for? There are various ways one could do it, but you would be looking to see someone having at least made an effort. So, questions?
Okay, that's great. That's some really good tips and tricks from your experience, Rob, and it's interesting to see those. And these are real examples of reports that have been circulating and are out there in the public sphere. So
Not verbatim, no. There are elements of work that was done in those reports that has been, shall we say, rewritten, hypothetically put in, and maybe even collecting a few little fails under one heading where they might have been separate. So generally, you wouldn't find exactly out in the multiverse precisely those words that I've been showing.
Yeah, no, that's okay. We do have a question there that is there a guideline on sampling regimes and best practices that can be implemented on site?
The document prepared for the Mine Rehab Commissioner, that's the basis of today, does have advice in there on sampling intensity for stockpiles, and there's various publications that for soil survey give guidance on sampling for if you're just doing a soil survey for different purposes. So there is information, yes.
Okay, that's great. I think we have one more coming through. I think that number you're referring to, Rob, was is that where the paper talks about a minimum of one sample per 10 to 20,000 cubic meters?
Yeah.
Okay, so that's a good rule of thumb, I guess, to use. Is that something that would need to be varied on a site by site basis? Or it's more of a blanket kind of just a general rule that's suitable?
I would be interested to see the argument that would be mounted to change it. You would be more likely to argue that you would increase the intensity of sampling above that if you had reasons to believe that the material in the stockpiles was highly variable.
Okay.
For example, in terms of reducing it, the argument that we've sampled 3 stockpiles and they were so uniform, so we'll reduce the sampling, just means that the very next stockpile won't be uniform. But I don't, as I say, I can see instances where you would sample more rather than instances where you would sample less.
Yeah, okay. And then depending on that variability, that's there. And okay, we have a question from Peter Berghofer. Thanks, Peter. The question is, what are the advantages of calibrating models with field erosion plots over lab erosion plots? Might be one for both of you guys, Evan, as well.
In the field, you get to get a longer term look at the processes. You get to track the materials through a range of conditions, and if there are any short-term changes due to wetting and drying consolidation, they're easier tracked in the field. The only thing you need to worry about, apart from possibly things as arcane as having damn dingoes dig up the wiring or something, is that the plots essentially can, if you have high levels of erosion, the plots become exhausted of sediment, which means that their erodibility actually changes. So if plots are subject to high rates of erosion, you can't run them for too many years.
Okay. Yeah.
I think it also picks up some of the practicalities of constructing landforms. So when you're building a large field plot, you can sort of see the impact of ripping, different ripping techniques, those sorts of things. I think even the role of vegetation, which I believe we'll get to next, but you can even look at quantifying with the vegetation on site what that impact is on infiltration and therefore runoff and erosion potential, that they're easier or more demonstrable within field plots. The lab plots really are great because they you allow for quite controlled and simpler ways of getting the parameters that are needed, are way more cost effective in terms of getting the data quickly and cheaply. So that's why I think both of them have a role. The other thing that erosion plots can be used is that validation process. So we talked about there being that closure planning phase, and erosion plots, if set up properly, should be able to not only give you like an erosion rate, but you can actually get runoff rates and even rainfall rates if coupled with the right sensors. So that gives you a data set you can then fit models to and validate the setup as well.
Yeah, yep.
The one last thing that Evan triggered for me is that if you've got large field plots, you can apply treatments to those field plots that you cannot apply on a lab plot.
Yeah, so they're just not comparable necessarily.
Oh, lab plots are too small sometimes. Yeah.
Yeah, the scale issue.
Yeah.
Yep.
All right. We've had a couple of questions come in, but I might hold those off because we're ploughing through the checklist and beyond halfway. So we'll hold those until the end. Thanks, Rob.
Okay, now I've put this in just to explain for those who might read reports that there are, in terms of considering the impacts of vegetation on erosion and on a landform design, the modeller or modelers typically would be left with two approaches. One was where basically they've got next to no guidance to work off. So in desperation, they simply identify what vegetation level is needed to achieve stability for a particular design. And you put responsibility for achieving that level of cover back to the site, which is fine. In fact, they may even give the site different landform and cover combinations, and the mine can decide which landform it thinks it can successfully stabilise, given how much veg they think they can grow. So there is a bit of a question mark there, and in that case, a regulator looking at the design may well put a condition onto some approval that suggests that the mine get out and find out how much vegetation they can reliably go so that can feed back to the landform design. Now, alternatively, a design report can or may focus on a particular vegetation cover level if there's monitoring to verify that cover level is going to be reliably achieved. So, yeah, the modeller has choices, but much of that is based upon whatever information the modeller can get. Okay, next one. So we have a look at this one, and again, if you say it quickly, this sounds quite credible. Cover establishment of 70%, including leaf litter and canopy, is considered to represent a well-established vegetation community within the region. Right. But does someone old, cynical and grumpy believe that? Well, first response would be, well, please show me the evidence. It's really, first up, please give me some verification, not just an assertion. And it is considered that one is a red flag to anyone who's read too many reports. That immediately fires up the desire to put red pen somewhere. Then you've got the questions of leaf litter and canopy cover. Wonderful. And is there a distinction between canopy and contact? Because canopy cover can be very ineffective on a steep slope. All the action's happening down where a flow is roaring across the soil surface, and leaves waving in the breeze 3 metres above that don't seem to do much to help. So you'd want to know a little bit about that. And then, of course, you've got the other key question: is there any evidence that mine rehabilitation is going to achieve the cover levels that are consistent with the region? Again, can you prove? This is all really about asking that the report lift its standards and avoid slipping in all of these unverified assertions. They need to be justified. Oh, this is a goodie. I can think of one regulator that's going to be happy this is in. So simulations used wet parameters used for rocky waste and topsoil. Surface contact cover, veg and rock, was of 90% has been measured. Again, well, it sounds like they've got some data. Sounds as if they've got lots of cover. Must be great. But the question and the concern right here is that basically somebody's just been caught double dipping. The effects of rock and erosion are accounted for in the WEP input parameters, so not fair to go and then want to add them in again as part of a cover factor that you might use to reduce your model output. So this means really that the person who did the modelling will have to go back to their simulations, change whatever cover factor they used, and with an altered cover factor no longer considering rock, the model output may not look quite so rosy. But anyway, thus it goes. Next one. Ah, yes. We're turning now to climate. And here we have a 9-year duration climate sequence based on daily recorded rainfalls from the site, which rings some good positive bells, but is it good enough? And there would immediately be the questions. How do the rainfall amounts and erosivity during that 9-year period compare with the long-term average? If they didn't, well, A, how do you demonstrate that they are comparable, and how, if there is a difference, do you account for it? So these things are important. Just go to the next slide to demonstrate why. Now, this is data from a long-running experiment in southern Queensland, Black Kraken Clays, eastern Darling Downs. What the graph shows is annual, it's called soil movement, but it means erosion. It's how much soil deposited in the contour bank. And you can see enormous variation from year to year. In fact, throughout that particular period, 14 years, there were only 6 storms that contributed 70% of the measured erosion. So bearing in mind the dominance of large storms on erosion amount, you start to see why we can get enormous variation from year to year. So the period that used, a short period used to look at to use rainfall data, does have quite a risk of being very far from the long-term average. And you just to raise a few warnings, there does need to be a review of how meaningful the 9-year period was, but there was very poor correlation in this particular experiment between annual rainfall amount and erosion. So in other words, the model has to try a bit harder if they're to consider. So there we go.
That's great.
We're through
Thanks,
to
Rob.
questions whether I like it or not. On you, Sam.
We're nearly all the way through.
Yeah.
But it's good to talk about climate variability. I think that is something it's a perennial issue that keeps coming up, and it's difficult to find the right way to manage that. And the discussion around vegetation effects and not being too heavily reliant on that, and being able to justify the numbers that are being put in, I think they're really important points. Evan, did you want to expand on any of those in this break?
Yeah, look, the only thing that came to mind, I suppose, just around that climate variability is that it can even be more variable in arid zones. So I know in situations, say the Western Australian goldfields, there's periods of 4 or 5 years where essentially no runoff occurs because the rainfall though it might occur, it just doesn't run off, and therefore erosion can be very sporadic. I've seen several cases where there's a decade or more between erosion events, So it does sort of beg the question that that the length of that record does need to be considered, and more so not so much just rainfall volume, but the actual erosivity or the storm energy or the energy of that rainfall is really, really important, because it's really what is more closely linked to the runoff and erosion, is just the intensity. So you might have a storm at, a 20 millimeter storm that occurs over 5 hours versus 24 hours. They're going to have different amounts of energy, and they'll translate into different amounts of erosion. So these things are important to see in the reports, that the modeler has thought that through and has addressed that.
Yeah, absolutely. And thinking about where the site is and what the climate is there, and talking to that in the report.
Yeah.
We have a question from the audience on climate that's worth asking here at this point. So they ask, what is the recommended climate duration to consider in the model? In terms of duration, I guess how long is long enough for climate?
Or however long is short enough might be the other way of looking at that as well. I think the meteorologists would say in the order of 20 years as a minimum length, as a minimum length of record. I know the Bureau of Meteorology looks at defining a suitable period of about 30 years. So I think it's in that sort of range minimum. So that's where your 9 years would be quite low. We at Landlock would typically adopt 100 years, and often that's because people like to get a feel for what, say, a 1 in 100, or at least some of those more rarer events are going to occur, and what they do as well. So I think it's in that sort of ballpark that we would consider. I suppose that because also the modelling is targeted towards a long-term average annual rate. As you go longer and longer with your rainfall record, the average annual erosion rate starts to settle and doesn't change as much. So there's potentially not much benefit in going sort of for really, really long climate sequences, because that average long-term annual rate doesn't then actually change as you just add more rainfall events into the sequence.
Yeah. Yep. Now, that's a great answer. We have another slide on model outputs, Rob, and then we might then pull up for a broader Q&A.
Okay, this one's a little bit of an orphan here on its own, but finally we get to the output of a modelling and see what on earth the modeler is made of it all. So you're going through, and again, you're checking that, because these should be discussed, were the targets adopted appropriate to the risks and the accuracy, and then think, do the outputs clearly identify the issues as being important? And at this point, I would remind everyone of the advice from the guy who was the leading US erosion modeler for many, many years. And he said, the first question that you ask when you look at model output is simply, does it make sense? And in this question, looking at addressing issues and coming up with conclusions, the obvious point there is simply, is the output and the way it's being used and applied making sense? So that is something that you really need to bear in mind. Then you can think, if a modeler can find on-site observations or data to validate or justify the model output, then those are great. You wouldn't expect them. Certainly, I know if I go to a mine site, I'm always very interested to see eroding areas and seeing different materials eroding and the rates, to try to get some feel for what happens at the site, even to get a feel for the things that are basically the cornerstone of stability or not, and whether or not the model output agrees with that. Some sites are stabilised by vegetation, some are stabilised by rock, for example. Then you look at if the model output is thoroughly interpreted, if it's been applied. Nothing more frustrating than to see that a report that says, we ran the model, here's the data, and no further comment. You're thinking, yeah, what do you make of this? You expect to see something. So you expect to see some interpretation, and you would even expect to see some discussion of, perceptions of limitations to the data identified, and are those limitations addressed? It might be that, we've presented data that we're very confident with in terms of the erodibility of the soil, but have information on, for example, vegetation growth is a bit sketchy, and that might be a matter of concern, or it might be questions about the depth of soil. So there are all of these questions that you can ask and try to think about. Am I happy with this, or does for some reason it cause me a worry? And on to the last slide. There we go.
Okay, that's great. It's a good point to stop and I guess reflect back on the work that's there. I really like the checklist. I think it's a fantastic way to take what's in that process that's done through the modelling and then turn that into something that people can apply from different sides of the industry that are out there, and being able to step through what needs to be presented in that. So it gives a consistent approach and methodology that can be applied by miners, by consultants, and by regulators. It gives us some clarity in terms of the expectations for a report and what we might want to see. And it should lead to some efficiencies in making sure that the information is there and it can go through the process more easily. And ultimately, better communication within landform design and more effective engagement in that process as well. So we have some questions from the audience, and there's one here from Christopher Wright. Would models be able to accommodate change in weather patterns, specifically extreme weather patterns? So continuing on that theme from the climate variability. Thanks, Christopher. That's a good one.
Evan, you first, maybe.
Sure, I love to. So yeah, the different models are able to. So for example, with WEP, within the actual WEP sequence for the climate, it actually has every day with a different amount of rainfall. Most often it's zero, but when there's rainfall that happens on a particular day, the model is able to then give parameters that then describe the intensity of the storm and the amount of the storm and the duration of the storm. So in that way, the sequence then can contain a wide range of storm events, and that would include extreme events and rare events that can be modelled. So that definitely has that ability. Often we look to model out a long-term average, but you can pick apart in more detail some of these outputs to then look at how it would perform under particular range of events or extreme events or what have you.
Yeah, I'd add that with Siberia, which runs on an annual time step, generally there's not a lot of facility to run a single extreme event. It's possible to run Siberia for a shorter time step, and but you would basically have to model the event with another model to know how you might alter the Siberia parameters. So I know there's been studies, for example, using Siberia that have looked at running the model for simulating the first year or two of a rehabilitation, developing a channelized landform, and then taking that particular channelized landform and then running it for a different set of surface conditions, just to see whether or not, for example, if you get a lot of rills develop early, whether they persist. So there's a range of things can be done. Some of it is just how energetic and inventive someone chooses to be.
Yeah, no, that's great. I'll move on to the next question from Emma Ryan Reid, and that's about target rates for erosion. Question is, should target rates be based on reference or analog within the local environment to be justifiable? So, yeah, is it justifiable to have target rates from your local environment?
I suppose it's similar to the natural erosion rate sort of
Mm.
conversation that we've had previously. So I suppose the response there is that it all depends on the natural erosion rate that you're wanting to pick. So for example, in coal where it's really flat, the natural erosion rate might be really low, and the hills might be really steep, but controlled by rock, and it would be very different. So I think pegging it to different natural erosion rates just has to be done with great caution, because it may actually not reflect what you have on your landform. I know Emma probably more interested in the Pilbara region, knowing Emma, and we did a study that was reported at the Mine Closure Conference at some stage. I want to say 20 something or other, 18 or 19, where we looked at acceptable rates through the Pilbara and found that that it was interesting in that case that the natural erosion rates were actually somewhat similar to the rates that generate low rilling or low tendency for gullying. So we did do an assessment in there, and some discussion in that paper might be useful to have a read for those who are interested.
Yeah, in general, the issue is very much that the mine site landform that's being modelled and will be rehabilitated is not a natural landform.
Yeah.
So taking an erosion rate from a natural landform and setting as its target, I would question why you would do it, and why you would not simply set an erosion rate such that your unnatural landform did not erode at an unacceptable rate. Anyway, different point of view.
Yeah, we also talked about risk in terms of erosion rates. There's a question from Thomas Baumgartel, which says, which of the risk factors is commonly the most sensitive from your experience?
Oh, thank you, Thomas. I don't think I could pick a favourite. I really don't.
Maybe site specific, would that be true?
Very much so. You can get very ugly materials. You can get people in central Queensland will blanch at the thought of having a tertiary waste sitting on or near the surface. In some instances, in numerous instances, slope steepness and length can be major concerns. I don't think it is very site specific, and the intent of the risk table is just to make sure that somebody goes to a site and are thorough in considering all the things that might go wrong. And I think it's worth considering them.
I think given that there's a tension, I think, between what mining wants often and what rehab and closure wants, in that mining often or operations, I should say, really has a desire to want to build things that are short haul and small. So they want to go steeper and longer and those sorts of things. And I think there's often a tension that I see there. So for me, often things like gradient and slope length are issues, and ultimately the overall height of these landforms is a common one that I come across, that is often putting these landforms into the high risk category.
Yeah. We also have a question from Peter Berghofer. He says, hi Rob and Evan, in reference to question on table 2 regarding the depth of growth medium. So with knowledge that the Bowen Basin is running out of topsoil, it is specified as low risk with a depth of less than 30 centimetres and high risk greater than 30 centimetres and a high risk of less than 15 centimetres. If the material is of a replaced topsoil is highly erosive and more so than the underlying material, would having a deeper layer of topsoil not be a liability?
Probably so. One of the things here is I would hope that risk assessment should be applied with a certain amount of thought applied. In that whilst it's suggesting something, if a site has got data that says that putting a shallow layer of topsoil gives us huge rates of runoff and erosion, well, that should be in the risk assessment. There is nothing about the risk assessment that says someone shouldn't include their knowledge and of the site. And if they've got extra information, it would be totally short-circuiting or ruining the process if you weren't to add that in. And I'm well aware in the Bowen Basin the discussions of topsoil usage and the shortage thereof are getting, shall we say, more and more pointy and more important. So I fully appreciate the reasons why Pete asked the question.
Sure. Yeah, Evan, did you have a thought on that? Or
no, I think Rob covered that up.
yeah, no, that's great. I think there's some flexibility in there around those site-specific considerations and being realistic there is important. So thanks, Peter. That's a really good question. We have another question from Melissa Salt. You've mentioned average a number of times. The Bureau of Meteorology recommends the median is average for climate data, whereas many consultants would use mean without thinking about it. Do you have an opinion as to whether mean or median should be used for average when it comes to erosion?
The point in part is that the models have an opinion.
On what they need to accept as
input?
No,
in terms of the output they give you.
Right.
So the universal soil loss equation gives you a long-term average.
Right. Yeah.
Thank you, Walt Wishmeyer, but that and in terms of WEP, one of the things it will give you is a long-term average. I might add that WEP gives you one option is to get annual data, and you can look at that annual data and calculate a median if you choose. Most people tend to pull up at the having grabbed an average and run. Now with Siberia, you get a cumulative erosion, and you don't get an amount of erosion per year. If you were obsessive about it, you could run the model for 1 year, 2 years, 3 years, 4 years, out to 200 years if you were seriously obsessive, and you could work it out. But it's generally people will simply look at the cumulative soil movement and they will take it from there. And because Siberia is actually applying the same amount of runoff and erosion each year, there doesn't seem to me to be the same justification for using a median to encapsulate variance in the data. So anyway, that covers the options. For the word on climate, however, I'll pass it over to Evan.
Thanks. I actually always thought Bureau used mean. Actually, mean average rainfall is a very common statistic that it pumps out. I think for me, so long as you understand what it is you're trying to measure, and you're then using a target that is the same measure, then I would be happy enough with that.
Okay, I think that covers that one off. That's good. We also have a question from Michael Frankham. He asks, is it possible to apply WEP and Siberia Siberia process to geomorphic landforms to achieve tolerable rates of erosion given concentration of flow and long, steep slopes? Thanks, Michael. That's a good one.
I'll say yes and leave it at that. How does that sound? No.
Please explain.
Yeah,
Please,
I would
okay, want some explanation. So certain geomorphic landforms, are growing in their desire or their desire to have geomorphic. I think one thing the industry hasn't yet done is to define what they actually mean by geomorphic, but it tends to mean more complex shapes. So with movement away from simple linear shapes and to more three-dimensionally complex shapes. So yeah, there's tools that allow for those shapes to be created, but they don't actually have an erosion component to them. The ones that are commonly used are trying to replicate the hydraulic the hydrology of the surface, which may be very different from a natural bit of ground, because you're now dealing with a pile of unconsolidated waste rather than a hill that might be controlled by a rock or what have you. But there's nothing to stop you from taking a more complex shape that's generated with another tool, and then using WEP or Siberia to then assess the suitability or the erosion potential of those complex shapes. And I think that would be a really useful thing to do as we move into more complex shapes, to have that check that what is happening isn't then leading to increased erosion. Because often the other thing that I'd say is that geomorphic shapes ultimately tend to concentrate flow over the landscape, and we've seen in history that by doing that in mining contexts, that's where gullies will always form. So if we're going to go that way, then we're not wanting to create landforms that concentrate flows to such a point that the critical shears are exceeded and gullies and rills start to form. That would end up being a failure of a landform.
Yeah.
Now, certainly it is possible, rather than use software to mimic a landform, which may or may not be relevant in any case, it's possible to use WEP simulations to come up with slope rules, where you might come up with a rule for a essentially concave slope, being careful to make the rule looking at not slope length but discharge versus gradient. And there are people around like 3D Data who can take that rule and they can make that into a complex landform. And then, having used that sort of software analysis and 3D skill to create a landform, perfectly possible to then use Siberia to assess the stability of it. So, yep, the two models have a lot of possibilities and potential.
Yeah, okay. That's great. It's really good questions and interesting discussion. So we have another question here from the floor. How would you recommend addressing vegetation cover in modelling outputs with programs such as WEP, which have a vegetation growth modelling component? And the second part to that question, do these veg growth components impact the validity of the results for these models?
Well, certainly from discussion with some of the American scientists who put WEP together, our view was that we don't actually try to use the growth component. First up,
yeah,
it is possible to use the presence of vegetation and living vegetation and with relationships to account for the presence of the vegetation in terms of infiltration and runoff. And it is then possible to use info on the levels of cover that the vegetation produces at the surface to apply a cover factor to factor down your predicted erosion to account for the presence of that cover, which was very much the response to me years ago from the American experts. Now there is one site where in the last year or two we did field rainfall simulator studies, and we measured a lot of erosion properties of vegetated slopes, and we just ran the model for that, and we alternatively ran the model considering that we're looking at a bare soil initially, factoring up for presence of edge and considering cover. And the two approaches did give us quite reasonably close data and quite reasonable agreement. So to that extent, we can say that it does appear that those strategies do work. And no, I don't know of anyone that's held their hand up to run the growth model side of web.
Yeah, well, that's great. I have another question for you. So similar to the different types of modelling, should measured data also be reflective of the stage of planning and design? And should small sample size in planning stage with additional data collected at detailed design, or be collected at detailed design, I guess?
Yes, well, generally, I remember some old chap who'd been in the mining industry since whenever, and he said on reflection of his career, he could never think of a project where he felt that they had overspent on getting samples analysed.
Yeah, yep.
He
It's
could
really
think of
important, isn't
many
it?
projects that suffered from a lack of data. And I think the problem you have is to say, oh, we'll do a half sampling or a very low intensity sampling now, and we'll go and do it later. And later, for some reason, either it doesn't happen or it's done differently so that the two data sets don't align. And whatever, it ends up to some degree, people wishing to hell they'd just done it the first time. And I don't think, compared to many things that happen and compared to the costs of running a landform design study, an extra dozen or so or two soil samples is a trivial cost.
Yeah. Putting that work in up front and spending the money, I guess, and in a focused way to collect the right information sets us up for success, I guess.
Yeah, and but I suppose maybe a little bit different from Rob, but at the early planning stage, like when you're still looking at pre-feasibility, even trying to decide whether you're going to put the project forward, there might be cases where you do need to know what you're dealing with in terms of erosion risk, but you can deal with a higher level of imprecision or inaccuracy. So maybe in that case, it'd be fewer samples would be fine, and analogous to that would be exploration drilling versus resource drilling, those sorts of things, or soil survey done at a reconnaissance level versus a planning level. So I think there's probably that to say, but I think Rob's point's really important in that the two examples I just gave, they're always followed up with the more detailed testing. So never does the exploration drilling then not result in further drilling when you're actually mining. Whereas I think in the environmental space, often we do fight that battle that additional sampling is still required to prove up and improve the accuracy or the confidence in that data.
Yeah, yeah, that's excellent. So we're coming to the end of the question time. We have one here that is, I guess, reflecting on the different perspectives. So, what is the benefit of this work for consultants, mining companies, and regulators?
Could you repeat what you said earlier again, please, Jason?
So the question is...
No, not the question. There was a comment you made right at the very start.
Yeah, it does cover back through that, doesn't there? I mean, the great thing about this work is that we can consider that, it's useful for consultants who are preparing the studies, and also for regulators who might be trying to assess what they're looking at. So it helps set a standard there. I think also from the mining companies' perspectives, I think it makes it clear as to what the expectations are. So looking at a project scope, approving those, and trying to work out what's necessary and what's not, I think are all good aspects of that work. But yeah, if you wanted to throw your thoughts into that.
Well, I'd emphasise that what this can lead to is a consistent and thorough methodology for looking at landform design that can be applied by miners, by consultants and regulators, so that each should be talking to the other and all within the same framework of expectations. And there's a fair bit of clarity coming out of this in terms of expectations. And it's given a fairly clear guideline of what to expect from a report. So it tells consultants and mining people what should go into the report. Hopefully it'll make life easier, and there'll be a few regulators with smiles on their faces cruising through reports, happy with what they see, and not wanting to make the sign of the cross and get the priest in to exorcise the demons out of the report. So it should give that consistency and efficiency across the whole process.
Absolutely. Evan.
Yeah, well, I think the industry really values clarity in some of these sorts of areas. So I think the work that Rob's put into producing this document provides some clarity in this space around erosion modelling. I know it's even now it's already, because I'm a consultant, it's actually enabled discussions between the client and myself about what's the expectations that are actually there, and being clear on that allows for the work to just happen with more certainty, knowing that what's being put forward is going to be accepted and there's no holes missing and those sorts of things. So I think that certainty is really important, and I think it will also help improve our practices. That in modelling, some of those examples that have been given are basically real examples, and so if those sorts of practices are reduced and we're getting an improvement in the quality of the work that's being done, then it's good for everyone, because the confidence in the modelling is improved, the outcomes are improved, the environmental outcomes are improved, and the regulators have to probably have an easier job at regulating because they're overseeing more and more success rather than having to deal with failures. So
yeah, for sure. I think it really just shows how complex it is to actually undertake these, but having a basis to be able to step through, what the expectations are in a stepwise manner is really important. So I'd encourage everyone to download the report, have a look in the back, check through have a look at the checklist that's there, and see if you can apply it in your next projects that are coming up. But any final statements, Rob or Evan? Yep. Well,
I was going to say 2.5 hours of us is long enough.
Okay, that's great. I wanted to thank you both
Agreed.
for bringing your expertise and your experience into this document. It's been a great process, and I hope valuable for everybody out there. So I would like to wrap up. And in doing that, just wanted to provide some takeaways from my perspective. So really, I think we can see that the model should be data-driven, and we need to accurately represent the materials that are present and the situations that are there. The erosion processes need to be considered properly. We want to look at the development of rills and gullies as well as a key issue in that. The models should be fit for purpose. There's no point doing more than is necessary, but they do need to be an appropriate standard to represent the erosion that's happening on site. They need to be matched to the stage of the mining, from early on through to middle of mining and approaching closure. You have different types of modelling there. And there's the need to apply the checklist and ensure that all the aspects of leading practice are covering off. So I would like to thank you all for joining us today. It's been a great turnout to this event. And finally, I would point you to a survey that we are preparing. So your feedback is important. Please scan the QR code on your phone using your camera. It will take you to a very short survey. It gives us an opportunity to understand, what work is working, what isn't working, what we can do better in the next seminar. So there were a bunch of questions that we weren't able to get to today, so apologies for that. But please keep the discussion going, and feel free to email the QMRC inbox. There's a link through our website to do that, and we can follow up those questions with you. Finally, on our website as well, there's a mailing list that you can join to register events like this and others into the future. So thank you. I hope to see you at the next QMRC event.